Okay, so couple ways to do this, guys. I'm going to show you the way that I think works best and that will work best for you long term first, okay? Then I'll show you the other way after that, okay? I want to calculate slope y equals mx plus b, okay? Which part of that formula represents slope? M. All right, need to get m by itself. Y minus b over x. Is this the same as the other way I'm going to show you after? Rise over run. Okay, so my y-intercept, b, is 0. That's great. Okay, this is going to make this really easy then. All right, and then I'm going to pick another point here. This one here I think looks really good because it's a grid intersection. It also happens to be a point I plotted. Okay, so I'm going to use those two values, okay, for y and x. So I'm going to have 1200 minus 0, okay, over 400. Okay, and remember we don't have an x2 under here because x at b is 0. All right, so 1200 over 400 should give me a slope of $3 per number, right? Okay, or some people might have said dollars per unit, okay, because that's usually what you say. If you're producing a bunch of things, you're producing this many units, it'd be dollars per unit, okay? Dollars per item, yeah, okay. Essentially, you can have anything that describes a single unit, okay, of something, all right? If these were teddy bears, it would be dollars per teddy bear. I don't know, $3 per teddy bear, I don't know, okay? Something like that. Everybody with me on that? So here's your marks distribution, okay? We said that that one would be out of 4 marks. So 1 mark, 2 marks, 3 marks, 4 marks, okay? Now, the other way would be to have rise over run, which essentially would just have a mark for slope equals rise over run, y2, so we'll have this, okay? Slope equals rise over run, okay? So that would be 1 mark, and then your other mark would be for y2 minus y1 over x2 minus x1, okay? And then the other marks are the same. The points that they plotted. Obviously, these numbers don't have to be the same as mine. Okay, they may have chosen different points than mine, and that's okay. Okay, so whatever numbers they plugged in, and then the slope should be the same. We all used exactly the same best fit line. We should all get $3 per unit. Okay. If they don't have units, it's wrong, and that's not half marks. I told you guys that on the last quiz, no half marks, and I got like 7 quizzes that still had half marks on them. You just realize that only makes you and that person feel good. I take it away, and then I have to feel bad. Don't make me feel bad. Okay? Peter. If they don't have it and they got the answer right, still give them full marks, but I like people to show all their work because if you screw something up along the way, I like to be able to give you part marks. Okay? All right. Second question. Okay, so we've got this graph here of temperature, listening please, of temperature and time. Okay, we want to calculate the slope of this one, all right, and we'll start out with y equals mx plus b. Okay, I'm going to find out what b is. It's right here. Okay, each line looks to be worth 2.5, so my y-intercept is 17.5. Okay, and then I got to find a grid intersection to use. That one right there looks like it'll work for me. Okay, so I'll have those points for my slope calculation. So again, 1 mark for this. Okay, 1 mark for y minus b over x equals m. And then we'll have our y value here, which was 5, minus our y-intercept, which was 17.5. We're going to get a negative number here? Is that okay? Yeah, the slope goes down, right? Okay, over x, the x value for this is 0.2. All right, so that's 2.2 for the x value there. Okay, so 5 minus 17.5, and again, their numbers don't have to be the same as mine. They may have picked a different grid intersection, and if they did, that's fine. We're using the same line. We're still going to get the same number here at the end. Okay, so 5 minus 17.5, okay, gives us negative 12.5 divided by 2.2, okay, gives me a slope of negative 5.7, we'll say. And my units are degrees Celsius per hour. Question number. They must have misread the scale on the graph. Give them all the other marks, but not for the slope. Because we all use the same line, we should all get the same number here. Okay. All right. So again, marks are the same as last time. Okay. If they used rise over run, okay, then obviously the first two marks will be, okay, for slope equals rise over run. Okay. Y2 minus Y1 over X2 minus X1. Okay. And again, we should get the same numbers as long as we're using the same line, which we are. I just finished saying that. Their numbers might be different than mine because they may not have used the same grid intersection. Then they don't get the mark. They don't get the mark for the answer. They'll get this mark, that's fine. Okay, but not this mark. Okay, any other questions? It's out of 8. The whole thing is out of 8. Okay, so mark out 8, let them see it, put it in the box. All right. So we're going to be talking about essentially two different kinds of graphs today. Okay, we're going to be talking about position versus time graphs, which you'll really want to pay close attention to as you had to make one for your lab. And I might possibly give away some really useful information on how you might use that graph to answer the analysis question from your lab yesterday. Okay, if you're listening carefully, you'll catch that. Okay, and the other kind that we're going to be dealing with is a velocity versus time graph, which we'll use in a different kind of graphing activity a little bit later on. Okay, so those are the two main kinematics graphs that we're going to deal with. Okay, position versus time, okay, and velocity versus time. Okay, and we can get a lot of different information and a lot of similar information from both of these graphs. What we have to understand is, how do we get it? Okay, so we're looking at something we call in physics graphical analysis. Okay. All right, so we're going to understand what kind of information we can get from those two graphs. Look at how the graphs that we're using are actually where the equations on your formula sheet come from. All right, and we kind of looked at that a little bit just briefly the other day with our position time graphs. Okay, and okay, that's the last thing there. Okay, so for a position versus time graph, obviously the purpose of a graph is to show information visually. Okay, instead of looking at, let's say, a chart where the relationship between the numbers is maybe tougher to see, okay, because all you see is the numbers. When you see them put on something visually like this, it's very easy to tell what's going on at a glance as opposed to having to do a lot more analysis. All right, so right now this graph is showing the position of the object, in other words, where it is, at various points in time. All right, so I can read directly off of this graph where the object is at any point in time. Agreed? All right. What other things do you suppose I might be able to calculate from this graph? Okay, I'd probably be able to calculate the object's velocity. Anything else? Philip, was that what? Okay, speed, velocity, yeah, be able to calculate both of those. What else? If I can calculate velocity, that means I can calculate one of the things I use to calculate velocity, which is displacement. Yeah. Okay. If I know where the object is at all these points in time, I should be able to calculate the displacement between any 2 points, right? Okay. So looking at this graph, what's the object doing in this part of the graph? Peter? Right. It's not moving because its position at time 0 was 20 meters and its position at 1 second was 20 meters, didn't go anywhere. Okay, so on a graph like this, anytime, or on any graph for that matter, a flat line generally indicates that whatever's on the y-axis is not changing. Okay, that could mean, if it's a velocity versus time graph, that the object is traveling at a constant velocity and not accelerating. Okay, on this graph, it actually means that the object's not moving. Okay, If it was a graph with mass on the y-axis, it would mean the object's mass isn't changing. Things like that. Okay? Now, what is the object doing between this point and this point? Going forward. Okay, is it accelerating forward or moving forward at a constant velocity? It's moving at a constant velocity. How many people were looking at that line and were liking the acceleration answer? It's okay to say so. Okay? A lot of people will give me that answer on a unit exam. I'll give them this graph, and they'll see that something's going up, and our mind immediately goes faster. Okay? It just automatically thinks that. Okay? But in this case, it traveled 20 meters in this first second, agreed? Okay? And how far did it go in the next second? Another 20 meters. It went the same distance in each time interval, 20 meters per second. Okay? What did we just calculate there? We just calculated speed, or if we said velocity, it would be 20 meters per second forwards or positive. Okay? But the other thing we calculated and didn't even realize it was, okay, we went 60 minus 40 or minus 20 over 2. Did we just calculate the slope too? Okay, the slope of this graph is going to give me meters per second, which are the units for velocity. Okay, this is where the formula v equals d over t comes from. The formula v equals d over t is the slope of a velocity versus, or sorry, of a position versus time graph. All right, the change in position divided by the change in time. Okay, in other words, the rise over the run of this graph. Everybody all right with that? Okay, and you're going to find that pretty much every formula on your formula sheet is derived somehow, okay, from a graph that we're going to use. Okay, what's the object doing right here? Peter? Okay, it's going backwards, right? Its position went from 60 to back to 20. What's its velocity? Nope, it's going faster. How can I tell it's going faster? Just by looking at it. Without even doing a calculation, I can tell that this part is faster than this part. Yeah, okay, yeah, it doesn't go through the same grid intersections like this one. In other words, this is steeper than this one. If slope is velocity, the steeper the slope, the faster it's going. Agreed? Okay, and that's what I'm looking at here. This line is steeper than that one, so this is faster than that one. Now, granted, they're not in the same direction. This one's forward, this one's backwards. Okay, but this one's clearly steeper, so it represents a greater magnitude. Okay, greater velocity here. All right, if I wanted to calculate that velocity, I could use v equals d over t, or I could find the slope of that line, since they're the same thing. Okay, everyone follow me there? All right, so if I did that, okay, I could say I'm going to use this point and this point because I don't really have any good grid intersections to use. All right, so I'm going to say 60, or sorry, final one, so rise over run, this would be 2. Okay, so I would go 20 minus 60, okay, over, and this looks like 1.5 seconds. All right, so 40 over 1.5 is definitely going to give me a greater number than before. Okay, so yes, we're definitely going faster. Okay, that should be negative 40. I forgot to put the negative on there. Okay, negative 26.7 meters per second. Okay, in other words, it's going backwards. Everybody right with that? Okay. Okay, what is the object in this second graph doing? Michael. Moving forward, okay, it definitely is doing that. Its position is becoming more positive, okay? But look at what happens here. Each second, does it go further than it did in the previous second? Okay, if you go further each consecutive second, are you traveling at a constant speed? You are doing what? You are accelerating. Okay, so a curved line on a position time graph tells us that the object's speed is changing, because it isn't covering the same distance every second anymore. All right, so in this case, the object is speeding up. All right, if the graph had a curve that looked like this, the object would be actually, it's always slowing down on this curve. Okay, here's why. This is where the line is steepest. What is the line doing? Is it always getting closer to flat all the way along, right? So in this case, it's slowing down, slowing down, slowing down, and now it's stopped. Okay, so the whole time it's decelerating. Okay, all right. Now, I don't expect, guys, that you memorize this kind of stuff. I expect the idea here is that you learn what certain types of shapes mean, okay, and then you can apply those to any graph. Right? Right now we're just talking about what it means on a position time graph. Okay? But having a line like this, okay, on any type of graph indicates that there's a certain type of change going on. Everyone follow me there? Okay? Whereas a slanted line like this means that there's a constant change or a uniform change going on. Yes? All right, slope calculations, we've already done that. We're going to skip over that. Okay, here's another position versus time graph. Okay, what's going on in part A? Devin, what's going on in part A? Yeah, moving forward at constant velocity, or is it accelerating? Constant velocity, because it's not a curve, right? There's no curves on this graph, in fact, anywhere. So is there any acceleration at any point on this graph? No. Okay, what's going on in part B, Aiden? Right, in fact, it's not moving at all, right? Okay, what's going on in part C, Donna? Going backwards, constant speed? Is it going at a constant speed backwards? Yes. Okay. What's going on in part D, Nick? Not moving. Okay. What's going on in part E, Danielle? Okay. And in part F, Quinn, is it going faster or slower than part E? Slower. Okay. Not as steep, not as fast. Okay. The rate of change in this part of the line, okay, is not as great as the rate of change in this part because the line's not as steep. Okay, and that applies to any graph. Okay, the rate of change in part F, if this was any kind of graph, would be less than the rate of change in part E. All right, now I want to do a few types of calculations off of this graph. Okay, on a unit exam, guys, I often ask something just like what I just did. Okay, I'll show you a graph, and then I'll say, tell me what's happening in this part. All right, now for a graph like this, where it's got obvious positives and negatives, there's two different directions, I would say you should be talking about vector or scalar quantities when you're describing. Vector. All right, so in part A we would say constant velocity forwards. Okay, B we could just say stopped. Okay, part C we would say constant velocity backwards. All right, in a question like that, I'm not asking you to calculate anything. I'm asking, do you understand what the graph is telling you? Okay, everyone follow me there? Now, the next part would be calculate the following things. All right, and I would ask you that as well. Okay, I very oftentimes put a graph on a test and say, tell me what's going on here and calculate the following things. All right, what is the total displacement in part A? Okay, Andres. Okay, 6 meters. Forward, backward. Yeah, vector quantity. See, it's easy to lose a mark on a question like that, right? We just go, oh, well, it's 6. It's easy to tell because it went from 0 to 6. It's just 6 meters, okay? And we forget, oh, he asked for displacement. Displacement's a vector quantity. All right, in general, guys, you can calculate displacement, and this formula is on your formula sheet, by going final position minus initial position. And you're going to use that all the time on graphs. So you might want to write it next to the graph in your notes there, just so you've got it. Okay, displacement is final position minus initial position. So that's what Andreas just did here. He went 6 minus 0 is 6 meters forward. All right, what's the displacement in part B? Yeah, 0. Okay. Because the final position is 6 and the initial position is 6. So the final displacement is, or the total displacement is 0. All right, total displacement in part C. Okay, final position is is that negative 10 or 12? Boy, I think it's supposed to be 10 because my line kind of goes crooked there. But I have a tool to figure that out. Okay, it's definitely 10. All right, so our final position is 10 and our negative 10, and our initial position is positive 6. So the total displacement here, Cameron, is? Okay, final position is negative 10, initial position is positive 6. Negative 10 minus 6 is negative 16. Okay, negative 16, right? If I'm already in the hole and I spend more money, I'm more in the hole, right? Okay, all right, so negative 16 meters would be our displacement for part C. Okay, in part D, obviously, again, it's flat, okay, and so the displacement would be 0. Okay, in part E, we go from negative 10 to negative 4, right, so that would be positive 6. Okay, again, just do final position, negative 4, minus initial position, negative 10. You're going to get positive 6. Okay, and then obviously the displacement here goes from negative 4 to 0. All right, so its displacement would be positive 4 meters. Okay, what if I asked you to calculate the total distance traveled over the whole trip? Peter? Nope. The total displacement over the whole trip is 0. You're absolutely right, because final position and initial position are the same. But distance is scalar. Bill? Okay, I got to look because I didn't actually calculate it myself. Okay, so here's how we figure it out. We got to find out how far it goes in each section of the graph without direction, because distance is scalar. All right, we said here that this one was 6, this one was 0, this one was 16, okay, this one was 0, this one was 6, and this one was 4. All right, so 6 plus 16 is 22, and 10 more is 32. Philip was right, 32 meters is the total distance traveled. Okay, what was the average velocity over the whole trip? 0. And how many of you are going, how did he do that so fast? Okay, it's okay if you're thinking that right now, but here's how he did it so fast. It started and finished in the same place, so its displacement was 0. Since velocity is displacement over time, velocity is also 0. Okay? Sometimes questions can be very easy. That's the kind of question where on a test people are kind of stressed out and they start doing the math, and then when they get done the math, they're like, man, I just wasted 4 minutes on something I should have known right away was 0 and had to show no work for. How can you tell on a test whether you should show very much work? Yep. How many marks it's out of? You wouldn't believe how many times on a question like this I put this beside the question and I see like 5 marks worth of work. Most of it wrong. Okay? If a question is out of 1 mark, there isn't much to do other than write the answer. Okay? Always look for that. It's kind of one of those dead giveaways on a test. Okay? All right. What about the average speed over the whole trip? How would I calculate that? How did we calculate it before? Total distance over total time. Okay, we just calculated the total distance. It was 32 meters. Looks to me like the total time for this trip is around 17 seconds. Okay, so 32 over 17 is what, Philip? 1.83 meters per second. Need a direction on that or no? No, because it's a speed scalar. Right? Little things like that we got to remember. None of these calculations are very mathematically difficult. We just got to remember how to do them. Okay. All right, is that making sense? Okay, so we got, that's graphical analysis, being able to look at a graph and kind of see what's going on and be able to calculate certain things. All right, so what can we get from a position time graph? Position and time, obviously. Those are always the dead giveaway. If it's a position time graph, you can definitely get the two things in the title. Okay, second or third thing you can get, displacement and velocity. Okay, those are the things you can get off of this graph. That's it. You can't get anything else. Okay, distance and speed. I don't mention those because I said displacement and velocity. If you can get those, you can also get the scalar versions. But yeah, you're right. Okay. Now, once in a while, you're going to get a graph that looks like this. Okay? This object is doing what? Peter? Right, it's accelerating. It's changing its velocity. In part A, it's accelerating positively and it's going faster. Okay? But nearing part B, what is it doing? Go ahead. It's decelerating, slowing down until it gets to here, and then what is it doing? Accelerating backwards. Okay? And then, as it gets past C, it's decelerating, coming to a stop again. All right? This graph, guys, is essentially of this exact motion. Okay? Because for the first part, I'm making the marker go faster. I'm accelerating it with my hand. As soon as it leaves my hand, what's gravity doing to it? Pulling it down, slowing it down, slowing it down, slowing it down, and then it gets to kind of its highest point, and then it begins to fall back down. It starts to fall back down. It starts going faster again until I catch it. Slow it down to a stop. Okay? That's a graph of that motion. Now, once in a while, you get a graph like this, and it'll say, calculate the velocity at this point. How am I going to calculate velocity from a curved line if the way to calculate velocity is supposed to be slope? Right. Okay? You got to draw a tangent. How many people know what a tangent is? Okay? A tangent is a line that touches a curve but doesn't cross it at one point. Okay? Now, what we're essentially doing here, and I'm explaining to you the only thing I understood in university calculus, okay? Because what a mathematician sees when he looks at a curve is an infinitely large number of infinitely small straight lines strung together. Okay? It's like if you look at a low resolution picture, okay? You can see the pixels in it, right? Because that's how a computer makes curved lines. It just uses little squares. All right? And as long as the squares are really small, we can't see them and the edges and lines look smooth. But if it's a low resolution picture, the pixels are bigger and we can see the jagged edges that, you know, don't look as appealing. Everyone follow me there? Well, that's what a curve is. A curve is an infinitely large number of infinitely small straight lines, all getting steeper and steeper and steeper, or shallower and shallower and shallower, as the case may be. So what I want to do is find the slope of the infinitely small straight line that exists at point A. Okay? So the way I do that is I draw a tangent that touches the curve there. And essentially all that does is make that piece of the line longer. Long enough for me to do a slope calculation. All right? I'm essentially drawing a line that's parallel to the curve at that point. In other words, it would have the same slope the curve has at that tiny little point. Okay, everybody with me there? That's as much as I understood about university calculus. I passed university calculus by memorizing every example in the textbook and writing it down on my final exam and getting part marks for method. I kid you not. That is how I did it. Okay? I understood nothing in that course. Okay? All right. I don't recommend that as a method for success. Worked for me. I don't guarantee it'll work for everybody. Okay? I spent weeks memorizing the examples. All right. So here's what we're doing. At part A, if I want to find the instantaneous velocity, I draw a tangent line. Now you guys would use a ruler, but I can't use a ruler on the smartboard here. So we'll do this. Okay? And I draw a line that touches the curve, okay, at point A, and it should be long enough for me to calculate the slope of. Agreed? right? So it's pretty close. It's pretty close to the one they drew. I can maybe adjust it slightly so it's a little bit better. Whoa. Oh yeah, there we go. All right, so there, I just touched the curve at point A, but I don't cross it. Now I know that my line here is the same slope as the curve at that point. So now I find, okay, 2 points on that line, do a rise over run calculation. I can't use y equals mx plus b here. For what reason? Right, I can't find out what b is, okay, because the graph doesn't go into the negatives and my line clearly does. All right, so I can't use y equals mx plus b. I have to use rise over run. All right, so I'm going to use this point here and that point there. They're good grid intersections. All right, so I'll have 10 minus 6 over 18 minus 12. All right, so I got 4 over 6. Okay, so no, 0.67, not 0.75, 0.67 meters per second forward. Okay, that's how fast it was going at point A. Right? If I was asked to find the instantaneous velocity right here, would my line be steeper? Yeah, because it's accelerating, right? Okay, I would draw a tangent and calculate its slope. All right, what's the instantaneous velocity at point B? Okay, I'm seeing a few hands up. That's good. 0. Okay, we should know that for 2 reasons. Okay, first off, it was decelerating, 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 and then started going the other way. If you're going to change directions, do you have to stop? At least for an instant you do. Okay, you are instantaneously stopped at some point. Okay, and if I draw a tangent that touches B, what's the slope of that line? 0, right? It's horizontal. A horizontal line has no slope. Agreed? All right. And same thing for C. Okay, if I wanted to calculate the instantaneous velocity at C, I would draw, okay, that, oh, that was a terrible one. That's what I love about the smartboard. I can cheat. There we go. Okay. Let me bring that bottom down. There we go. Okay, and calculate the slope of that line. I'll have the velocity there. The velocity there will be positive or negative? Negative. Okay, it's going backwards there. Everyone all right with that? That's going to happen once in a while. I don't remember the last time I asked that on a unit exam. Okay, in fact, I don't think I ever have, to be perfectly honest. But it's still something you do need to know. All right. So for velocity versus time graphs, okay, velocity versus time graph and a position versus time graph show the same object doing the same thing. They show it from different points of view. All right. So in this case, these 2 graphs here are of the same object, undergoing the same motion. Why do they look different? Yeah, Peter? Right. Okay, the position is changing, but the position is changing at a constant rate. If you're changing position at a constant rate, you're moving at a constant, constant speed or constant velocity, which is what this graph is showing, is it not? Right? This is a velocity versus time graph. It's saying the velocity isn't changing. They are showing the same thing, right? But they're looking at it from different viewpoints. All right, now, I want to calculate the velocity. I could read it off of this graph, but it's not exactly a grid lines, and it's kind of hard to tell. I would be estimating. Can I get it off of this graph? Okay, how do I get it off of this graph? Yeah, I could use the best fit line, or in this case, since the best fit line goes through every single point, could I just do total distance over total time? Which is the same thing on this graph, right? Okay, so I've got 1,400 meters is my total displacement. Sorry, not 1,400. 1,300 meters is my total displacement, because this graph starts at 100. That's a dirty trick. Watch out for that. Once in a while that happens. Okay, the origin isn't on this graph. It starts at 100. So 1,400 minus 100 is 1,300. Okay, over 5. All right, so that's what, 265 meters, something like that. 260. Okay, so this value right here is 260 meters per second. Okay, what if I want to find the displacement of this object? Is that easy to get off the position time graph? Okay, what is it? Right, 1,300 meters. Okay, final position, 1,400 minus initial position, 100 is 1,300 meters. All right, how am I going to get it off of this graph? Right, okay. Guys, if this graph is showing velocity and time, it's using that formula, is it not? Okay, well, if I want to find distance, I would go like this, right? T times V. That's essentially then finding the area underneath my line. Okay, now, there's a couple of ways to look at this. One of the ways is, yeah, you could memorize that. Don't really like that, because by the time you get to Physics 30, you'd be memorizing like 65 different graphs. You don't want to be going into a 50% diploma exam having to memorize 65 different kinds of graphs. Okay. Instead, I could look at my units. Okay, which is what we just did here. We said, well, there's velocity here and there's time here, and the velocity's not changing. That means I can use this formula then. Okay, and that I can go and find the area underneath this line and go V times T equals D. All right. Now, what if the line looks like this? It's accelerating. Can I still find how far it goes? Yeah, that's what this formula says, right? This formula says average velocity is displacement over time. Well, there's an average velocity on this line somewhere, isn't there? Okay, now we just said that if I calculated the area of this rectangle, it would tell me the distance. What shape is that? Is that, okay, it's a triangle. Can I find the area of a triangle? Okay, base times height over 2. Okay, so if I do that, okay, I'm going to have the base is 3.5, and the height is 450, 550. Okay. Okay, so 550 times 3.5 over 2. All right. Right. The dirty trick again. 450. Okay. So 450 times 3.5 over 2. Now, if I know that my initial velocity, okay, is essentially 100, my final velocity is 550, okay, my average velocity would be exactly halfway between them. Agreed? Because the acceleration was uniform. Well, is that what I just did there? It is. Okay, it's exactly what I just did there. All right, and then multiply that by time. Essentially, I still did this. Average velocity times time equals d. All right. So whenever you're looking at a graph, okay, what you want to do is see if you have a formula on your formula sheet that shows the relationship between the two things on the graph. Okay, and if you can, then you'll be able to figure out what you need to do to calculate what the question's asking for. All right. Okay. What's going on in this graph? It's a velocity versus time graph. What's happening here? Stephen, what's happening in that part? It's accelerating. Okay. What's going on here, Shaylin? Going at a constant speed. Okay. And in this part, Emma Heeg. Slowing down. Okay. In fact, slowing down and coming to a, how do I know it comes to a stop? Well, remember, this is a velocity versus time graph. It goes down to 0. Okay, it's easier than that. Okay, on a position time graph, you're right. If the curve went down like that and flattened out, then I'd be stopped. On this graph, I know it's stopped because it got to 0 and is showing velocity on the y-axis. Okay, so yeah, there's little things. That's why it's dangerous to memorize, right? You see, oh well, this pattern means this, but it only means that on this kind of graph. Okay, that's the danger of memorizing, is that you'll start confusing the things between the two graphs. Okay. All right, you have these in your notes here, right? These two paragraphs? Just double check because these are super important, okay? In terms of what we can calculate from our velocity versus time graph. Now, the one thing that's not on here, okay, is how we calculate acceleration from a velocity versus time graph. Okay, so want to quickly have a look at that here. We'll just make one up. Okay, on your formula sheet, if you can just take that out for a second. What's your formula there for acceleration? I'll give you a minute to find it. The formula for acceleration. Hey, Cam? Okay, Peter? Right. Okay, this is what the formula is. Final velocity minus initial velocity divided by time. Okay. Can I get velocity off of this graph? Yeah, because it's a velocity versus time graph. I also have time on this graph. This is the change in velocity here, right? Final minus initial tells me the change. So let's say I had these 2 points on my graph. Okay? Could I say that y2 equals vf and y1 equals vi divided by time? Is that rise over run for this graph? Yeah. Okay. You can calculate acceleration from this graph because acceleration is the change in velocity divided by the change in time. Okay? And that's what the slope of this graph shows, is change in velocity divided by change in time. Everyone with me on that? Now, weird units for this. What do I get when I divide meters per second by seconds? Okay. Meters, yeah. Okay, we'll say it this way first, and then we'll talk about why it's meters per second squared. If I divide meters per second by seconds, I get meters per second. Okay? The rate of change of speed. Okay? How much my speed changes every second, meters per second. Okay? But here's how that looks when you do your, you remember back in like grade 8 when you got taught how to divide fractions? I know, it was scary for me too. Okay? All right, if I want to divide fractions, I reciprocate and, then I multiply. All right, so in other words, that means going meters per second times 1 over seconds. Meters times 1 is meters. Second times seconds is seconds squared. Meters per second is abbreviated as meters per second squared. Okay, but it's the units for acceleration. And acceleration is the rate of change of velocity. All right, we'll talk more about acceleration next week. Okay, but that's where it comes from. Okay. All right, maybe write something like this down here in your velocity versus time part of your notes there. Okay. something like that. It's kind of a jot notes kind of summary of what we just said there. Okay, acceleration can be calculated from a v versus t graph, velocity versus time, okay, using slope or vf minus vi over t. Okay, and that vf and vi, do they need to be on the line for that to be true? They do. Okay, sometimes you'll get a graph and it'll have a chart beside it and it'll show, you know, a bunch of these points here, and your final velocity might be kind of way up there, and your initial velocity could be this number over here. Well, those aren't on the line. Okay? There's a difference there. So that would be one of those questions where if it said, using your graph, do this, well, then it would be a slope calculation. If it says, using the data, then you could just use the data and go VF minus VI over T. Everyone follow me on that one? Okay, so little things there. Usually on a question, I'll boldface, okay, how I want the question done, right? Because sometimes I need to test a certain way. Everyone with me there? Okay, I'm going to hand out this graphing worksheet here that's got some graphs on it, just for you to practice, get some experience using different kinds of graphs to find different things. Okay,